Welcome everyone. Chapter 2, Section 5, the derivative of a composite function, also called the chain rule. It's on page 99. Now back in previous section, we talked about the power of a function rule, right? When we had to take the derivative of the bigger function, right? And then the derivative of that inside of that interior function here. That's because of the composition of functions. And way back to grade 10 review, when we have two functions and we notice that one's sort of a function of the other here, this is called composite functions. Okay, so we read it as f at g at x. Okay, and sometimes we need to introduce another a variable. In this case, u. I'm going to use a lot of u's and v's. I'm going to use a lot of in this particular section. So a given function is in terms of one variable, and then the second function is in terms of that other variable. On a mapping chart, okay, this is kind of what it looks like, and this is probably, I hope, how it was introduced to you back in grade, probably about grade 10 here. Okay, so here's our function. Okay. Oh my goodness. Okay, here's our function. Okay, f at x equals x squared minus 3x, all raised to the power of 15. Now, composite functions involve a combination of functions here. And I think it won't take us very long or very tough to realize that we've got, okay, a quadratic function, x squared minus 3x. I'm going to call that h at x over here. And then I've also got a function x to the raised to the power of 15. I'm going to call that g at x. Okay. Now the issue is that I should introduce another variable here because I've got a combination of x's and g's and x, okay, two functions in terms of x. So I'm just going to quickly call g, rather than call g with respect to x, I'm going to call g at u, and that would equal u to the power of 15. Okay, so when we look at that, we can look at the big function f at x as a combination of h at x, okay, that would be x squared minus 3x. And we can look at it in terms of a g, and then when I apply my function, my Mappy notation on g, all I'm doing is just taking this expression, x squared minus 3x, okay, putting it in through the g function, and then raising whatever that variable is, x squared minus 3x in this case, raising it to the power of 15. On Mappy notation, okay, this is kind of how it looks. We take our values of x, we put them through h first, okay, and then we get h at x, and then we take these values and we put them through g, and then we get g at h at x. Now this is complicated for students, okay, especially the process is easy. Okay, I think we pretty much understand that this function x squared minus 3x raised to the power of 15. We understand what it does, what it looks like, and how to work with it, right? When we get into notation, and specifically mapping notation, okay, this is where it gets complicated for students, and I don't want it to be complicated. Okay, I certainly want you to look at and understand how we deal with these functions. Okay, and we've been doing this. Okay, we've been doing this throughout, okay, the last couple of sections here. So how do we differentiate the following function? Okay, so we identify the two functions. Okay, something to the power of 15. Okay, so that's something to the power of 15. Well, what's the derivative of something to the power of 15? Well, it's 15. Okay, the something's going to go in my brackets, and then I write 14 here. And that something is x squared minus 3x. And then I have to take the derivative of that something function. Okay, now it's awkward to say call it something, okay? So, but either way, we get the point here. Okay, that something function, or that inside interior function, also has to have the derivative taken. Okay, and that's what I'm going to start calling it as, the outside function and the inside function. Okay, so now we've got this function 4. Okay, and then we've got a cubic. I'm going to call that my inside or my interior function. Okay, and then that cubic has been raised to the power of 3. So how do I find the derivative? Well, the 4 is just a leading coefficient. We don't worry about that 4. We just write that as part of that. Okay, so now I have to take the derivative of the inside or the interior function. Okay, and that'll be 3 then whatever that interior function is, and then I raise that to the power of 2. I'm going to close my bracket. Then I have to make sure I multiply it by the derivative of my interior function. And that, in this case, it's 3 times 3 is 9, x squared, plus 12x. Okay, now that's a pretty complicated, pretty serious function, but make sure we understand that the original function is pretty large itself. Okay, there's a lot going on in those original composite functions here. Okay, we've got to take our values x, okay, work them through this cubic function, raise it to the third power, and then multiply it by 4. The derivative is going to be a large, pretty large function as well, too. Okay, here about c. How do I find the derivative of c? Well, what I want you to do is understand that, or maybe try and start to see that there are two functions in here. Okay, so here are our functions. There's a quadratic, and then there's a square root function. Okay, so to find the derivative, I have to take the derivative of the square root function, and then I have to take the derivative of the quadratic function and multiply that across here. Okay, and that's my derivative of my composite function here. Now I should clean this up a little bit. Okay, okay, the 1 and the 2x minus 1 are in the numerator. Okay, and then I have a 2 in the denominator and a square root of x squared minus x. Now I can probably drop my brackets if I like. Okay, so did you catch what I did there? First things first is I recognize, and it really helps, I think, to recognize as I write a composite function, recognize the functions that make up the composite functions, the base functions are okay, or so there's sort of these basic functions that we're used to seeing. In this case, okay, we've got a cubic and then raised to another cubic. Okay, in this case up here, we've got a quadratic raised to the power of 15. Oof. Okay, and in this case down here, we've got a parabola, right? X squared minus x, then the square root function. So when I take the derivative, I have to take the derivative of the big function, right? The outside function. In this case, it's the square root. And then I take the derivative of the inside function. Okay, that's opposite of what derivatives are, okay, kind of related to, or they're derived from original functions. So if I was given the function, okay, the first thing I'd do is I'd work inside the brackets, right? If I was asked to evaluate this function, x squared minus 3x all raised to the power of 15, I'd evaluate inside the brackets first, then I'd work that out, and then I'd raise my answer to the power of 15. When I'm asked to find the derivative of the function, I work in the opposite order. I take the derivative of the big outside function, and then I take the derivative, multiply that by the derivative of the smaller function. These can get complicated, quite complicated, but again, practice, and make sure that we're good with this. Okay, let's do this one. All right, so it's going to be derivative of 10. Okay, so sorry, the derivative of 1 plus x squared over 1 minus x squared. Oh, that's a quotient. This is going to be a bad one. Okay, all raised to the power of 10. Well, I'm going to do the derivative of the function raised to the power of 10 first. That'll be raised to the power of 9. Then I have to multiply it by the derivative of my inside function. I need the quotient rule for that. All right. Let's just do a little side trip here. 2x minus 2x. So my derivative is going to be the quotient rule. Well, remember it. The second function gets squared. Okay, now I go 2x, 1 minus x squared, subtract negative 2x, 1 plus x squared here. I should clean this up a little bit here. I want to make sure that you guys can see that. Okay, and that was a negative 2x. Oh, I did it again. There we go. Okay, Now, could I simplify? Well, I'm gonna simplify a little bit, and just so that you know how to do this. Okay, let's expand that in. 2x minus 2x to the power 3 plus 2x, and then a negative times a negative, and a 2x squared, so that'll be a plus 2x to the power 3. And over one common denominator, it's going to be 1 minus x squared to the 9, and then another 1 minus x squared to, so that'll be a 1 minus x squared to the 11th. Okay, so that 9 has to go in here, like it did, and has to go in the bottom. Now I think that probably cleans up a little bit even better here. What have I got in the square brackets here? It looks like I've got 4x. Here's my all over 1 minus x squared to the 11th. Now the 10 times 4x, so you could easily be simplified to 40x. Okay? So it doesn't simplify down too bad. Okay, let's try the next one here. Given a function s at t, a displacement function, find the velocity at t equals 1. Okay, I'm just going to cheat a little bit and see if I could find my notes for this one. Okay, so this velocity is going to be my derivative function. Okay, and my derivative function, I've got t squared and 2 minus 3t raised to the third power. So I need the derivative of t squared is 2t, and the derivative of 2 minus 3t to the power of 3 is what I've just written here. I think I've done that right. I'm just going to double check. Right, so my derivative function is a product rule, right? There's a product in here. That's why I broke them apart. So I've got 2t, and then t minus 3, t to the power 3, plus t squared, times negative 9. I'm just going to multiply the 3 and the negative 3 together. And now I've got, okay, and that's my s at t. And my question asks me to evaluate it at 1. So when I evaluate it at 1, I'm just going to plug in every place there's a t. I'm going to plug in 1. Okay, so it looks like I've got this working out to be, I have in my notes, and that's a meters per second, okay, because it's a velocity. So at time t equals 1, the velocity is decreasing 11 meters per second. Okay, now notice I didn't simplify, right? I could have simplified here if I was just asked for the function, but I'm not. I'm asked for the velocity at t equals 1. So I calculated the derivative, that's the velocity function, and then I just simply evaluated that derivative function out at t equals 1 in order to get the answer I was asked to find here. All right, Leibniz notation. Leibniz notation is required in a couple of homework questions. Okay, so Leibniz notation, if I have to find the derivative of v with respect to x, I might have to find the derivative of v with respect to u, and then multiply that by the derivative of u with respect to x. Don't get bogged down by this. This particular Leibniz notation for derivatives seems to upset and bother a lot of students. But again, here's the chain rule idea, and we're just chaining that across here, that derivative function. All it means is I can't find the derivative of a v with respect to x until I find the derivative of v with respect to u, and then multiply that by the derivative of u with respect to x. Prime notation also works the same way. It's the same type of function. Okay, if we have a function raised to a power, okay, I find the derivative of the power function first, and then I find the derivative of that inside function here. Now we're going to practice Leibniz notation here in a minute. This is how I'm going to finish uh, the lesson here. Okay, so we've got u and v, okay, and I want to find dv dx. Okay, so I've got u in terms of x, so I can find du dx. Okay, and that would be 1/2 x to the negative 1/2. And now I'm also given v, okay, with respect to u. Okay, so I could find dv du. Right, now that would be a quotient rule. Now why I did that is because this is what I'm asked to find. I'm asked to find dv dx. But I don't have dv dx, right? I don't have v in terms of x. I have v in terms of u, and I have u in terms of x. So my intermediate, or my chain function, is this function of u. Okay, but I do know, according to Leibniz notation, that I could find the derivative of v with respect to u. I just did that right here. I'm going to do that right here. And I can find the derivative of u with respect to x. I just did that right here. Okay, and that would allow me to find dv dx. Okay, so let's finish this off. Let's find the derivative of v with respect to u. Okay, quotient rule. Okay, so it's 1 times u minus 1, take away u times 1, all over u minus 1 squared. Okay, so that's going to be u minus 1 minus u. Okay, so that's going to be a minus 1 over u minus 1 quantity squared. Okay, so let's bring these together. Now dv du. dv du I just found. And du dx, okay, now I have a value for x equals 4, right? I have a value for x equals 4. Okay, so I certainly can substitute that in. Okay. Now I still have my u in my original, the question that I've been asked to find, dv dx. I still have u. So what I need to do up in this case is find a corresponding value of u when x equals 4. Okay, now I can do that, okay, right here. Okay. So at the particular instance when x equals 4, the square root of 4 is 2, u equals 2. Okay, so now it allows me to substitute. Better make sure that that was what it was. I think so, yeah. Okay, so can I evaluate now? All right, so negative 1 over 1, okay, and then I've got, okay, the square 1/4 here, so I've got a negative 1/4. Good, and that's dv dx at x equal 4. Good, so that's not so hard, right? Using Leibniz notation, understanding this connection here, though, and understanding and giving due credit to this inside, or this connecting, this chain function across this u, okay, this u function here. All right, Lagrange notation here. Yeah, Lagrange notation is not a big deal. The chain rule with Lagrange notation, the derivative of the outer function multiplied by the derivative of the inner function. So let's do a couple. Let's do this one. Okay, maybe we've done this one already. I don't know. I don't think it's too tough. 5 x to the power 3 minus 2x squared plus x, and that's raised to the 4th power. And then just don't forget to take the derivative of this inside function. That's going to be 3x squared minus 4x plus 1. That's it. That's the derivative. Any more on this page? I don't think so. Nope. Right, composition of 3 functions. As you can expect, these can get very challenging. Okay, so the composition of 3 functions just has 2 chains across here. We've got connecting functions. Now our example, okay, we're going to be asked to do 2 things here. Okay, our example involves us to find the derivative and then evaluate it at x equals 4. All right, what's this function? This function's crazy. It's got three functions going on. Do you notice a square root function? Okay. Do we notice a reciprocal function, 1 over? Okay. And do we notice a parabola, quadratic function, x squared plus 1? So there are three functions. Okay. So our three functions. Now, in order to find the chain rule, or the derivative of this function, we have to find the chain rule. I use the chain rule here. The derivative of my function, okay, it starts with my original question. I have to find the derivative of, and I'm going to find it with respect to, okay, so this is asking me to take the derivative of the square root function, find the derivative of the square root function first. Then I have to chain across my reciprocal function. And I'm going to find the derivative of my reciprocal function second. So it's going to be with respect to my parabola. Okay, and then the last thing, I'm going to find the derivative of my quadratic or my parabola function with respect to x. Okay, so that's how to properly do the chain rule with Leibniz notation. Okay, now let's do it. Okay, what's the derivative of a square root function? Well, the derivative of a square root function is this. Okay, but now I want to make sure that I put in my function that I found. Okay, now what? Now we're over here. What's the derivative of a reciprocal function? What's the derivative of a reciprocal function? Okay, so reciprocal function, okay, is x to the negative 1. So the derivative is x to the negative 2. Okay, so it's going to be, I've got a negative 1 to the negative 2, and in here goes x squared plus 1. Okay, and now I've got to take the derivative of x squared plus 1, which is 2x. Okay, I think we've got that. Have we got that? Whoa, that's a lot. Okay, now how in the world do I simplify that? Okay, well, let's deal with some of these expressions here. 1/2, okay, 1 over x squared plus 1 raised to the negative 1/2. If I have a fraction raised to a negative exponent, I can flip the fraction and write my exponent positive. Okay, that's just the reciprocal of a reciprocal. This one is negative 1 over x squared plus 1, and then I have a 2x. Okay, now my 2's will cancel. My negative 1 I've got in my numerator, and I've got, and then I've got, okay, another x. I'm sorry, I should have had an x in here, so let me put that. Okay, and then I've got x squared plus 1 squared here in the denominator. Okay, now I can even go further, right? I could even go further because I have a common base to exponents here, so I could simplify that down to one expression. That'd be 1/2 minus 2. 1/2 minus 2 is 1/2 minus 4 halves, so it'd be the negative 3 halves. Okay, that's really a tough one. Okay, understand that that's how we kind of do it, and we work on that derivative here. Now I think the final answer required that we evaluate this at 4. Okay, so I've got, don't think I'm quite done yet. I think I've got, okay, so I've got negative 4 over the, okay, 17. 4 squared plus 1 is 17, raised to the 3/2 power. Okay, so that's a negative 4. over square root of 17 to the power of 3. Okay, again, that's a tough one, and you'll practice some of those in the homework questions. Okay, I think we've got one more to do. Got to burn through this. Yeah, this one, differentiate this. I won't simplify this one here. I think we've done maybe enough of these. We've got a big one here, though. So we've got an x squared, and I've got the square root Okay, this is an easy derivative. The x squared is 2x. This one's a lot tougher because I've got chain rule and then a quotient rule. Okay, so now I've also got to multiply that by the quotient rule here because I've got to find the derivative of that inside function here. Okay, so the derivative of that inside function, okay, is 1, okay, x squared plus 1 minus 2x, x squared plus 1 all over x squared plus 1 quantity squared. So f prime is now the product rule. Okay, so 2x okay, plus x squared 1/2 x plus 1 x squared plus 1 to the negative 1/2, okay, and then x squared plus 1 minus 2x squared minus 2x all over x squared plus 1 quantity squared, close my bracket, okay, and that's pretty large. Okay, that's quite a complicated function. If you got that, okay, you're rolling along here pretty good. And we'll work on some of those homework questions. That was a negative 1/2. Okay, okay, looks good. I'm just cleaning this up. I probably could clean that up a little bit here if I were to simplify this a little bit farther. Okay, for me though, as when I mark some of these and look at these, it's a lot easier to evaluate this. Okay, when it's non-simplified. Okay, I get to see that you do know how to do the product rule. Okay, this is I didn't even realize a product rule, quotient rule, and a chain rule all wrapped up into one. Okay, this finishes chapter 2, so I want to make sure that we do a lot of these homework questions, and you'll have a couple of days to get ready for the final unit chapter 2 assessment here, and we'll get caught up on some of these homework questions, okay, and a wide variety of review questions as well too. This is an important chapter, chapter 2. Certainly it helps us find derivatives quickly and really important application questions. Okay, good luck.